All right, I want to tell you right now, you are in for an exciting lecture tonight. Can we turn that off, whoever's phone is on? Somebody's dinging. Tell Dad we're getting ready for an exciting lecture. All right, are we ready? Okay, we need a clean periodic table. Yes, I know. Another one? Yes. You'll want a clean one, I think. I think you'll want a clean one, okay? So take a clean periodic table. If you want colors, there are some colors on the bottom. Go ahead and get out your previously marked on periodic table. And let's just do a couple of reviews. How many protons does chlorine have? Chlorine, protons. 17 protons, okay. How many electrons does strontium have? 38. Okay, good. Tell me how many electrons the chloride ion has. How many electrons does the chloride ion have? Chloride ion. How many electrons does the chloride ion have? 18. Why does it have 18? Because it has a -1 charge. Good. Okay, go ahead. Absolutely. All right, take a periodic table that's clean, and at the top of your notes, we're going to be looking at your periodic table and your notes. And at the top of your notes today, I want you to draw a line. At the top of that page of notes, draw a line about 1 centimeter down from the top of the page. So we're going to just draw a straight line. Okay? On the left side of the line, we're going to put gamma rays. On the right side, we're going to put radio waves. Somewhere in the middle, we're going to put Vib G your. What is that, by the way? Colors of the rainbow, okay. Over on the right side near radio, let's put microwave. And then let's put infrared. We're not really doing this to scale 100%. It's a relative scale. Next to violet, we're going to put ultraviolet. And then between ultraviolet and gamma, we're going to put X-ray. UV, by the way, is ultraviolet, if you didn't remember that. Now, I want to tell you that today's lecture is going to seem like it is very scattered, but I promise you, if you will stay with me, all of this will make sense, okay? But you've got to stay with me. Just put everything else aside right now and stay with me, because at the beginning of it, you're going to think, what does this have to do with anything that we're doing? let me back up before I get going on this and tell you our ultimate goal today, and we will make this goal. Our ultimate goal today is by the end of class, every one of you will be able to tell me where the electrons are for any atom on the periodic table. In other words, Lawrencium or Nobelium or Einsteinium, number 99 down there, ES. You will be able to tell me where every electron is located in ES before the end of tonight. And you probably will be able to tell me why chloride, for instance, we just talked about, has a -1 charge. You'll be able to tell me why it really does have a -1 charge, more than just, oh, it gained an electron. You're going to be able to tell me why did it gain an electron, okay? That's our ultimate goal. But to start with, I'm doing something that right now you probably think has nothing to do at all with it, but it does. So just bear with me, all right? What I've drawn up here is the electromagnetic spectrum. That's what you're seeing on the paper is an electromagnetic spectrum, and it's a relative one. It is giving us the wavelengths in relative position to each other, and then we're going to look at this related to frequency, and we're going to look at it related to energy. So let's first start with wavelength. Waves are measured from peak to peak or valley to valley. So let me just give you an example. The top of the door here, where the wall changes color, the door facing, the top of the door facing to the top of the door facing there. Let's say that that is the peak. And so that's the peak of the wave, and then the wave comes down here, and this is the valley, and it goes to that peak. You with me? Okay. To measure that wavelength, we would measure the distance from the peak to the peak. Now, comparatively, that's a relatively long wave. Would you agree? Okay. A shorter wave, so a shorter wave, that's a shorter wave, right? Just what I'm doing with my hand here, that's a shorter wave. Okay. Radio waves are long wavelengths. Gamma rays are short wavelengths. So write that on your paper. Radio waves, this end of the spectrum, short waves. I told you wrong, didn't I? Goodness gracious sakes. Long waves. Long waves. Long waves, radio waves. Make sure you write that right. Long waves, radio waves. Short waves, gamma. Long waves, radio waves. Short waves, gamma. And everything in between, that means microwave is a little shorter than radio. You follow me? All the way. So ultraviolet are shorter. You follow, okay? All right. Frequency is also determined relative to each other on this spectrum. Frequency is how often a wave passes a certain point. Okay? So in other words, if this is my point, all right, every time you hear the clap, that's when the wave is passing that point. You with me? Now, right now, I'm demonstrating for you the frequency of a rather long wavelength. Okay? What's that? Short wavelength. So, a long wave has, compared to a short wave frequency, a long wave has lower frequency. A short wave has high frequency. So low frequency down here for radio waves, high frequency over here for gamma rays. And last but not least is energy. How does this relate to energy? You tell me which one has higher energy. Did the low frequency have higher energy, or did the high frequency? Didn't you feel it? Didn't you feel the difference in the energy? So high frequency has high energy. So high frequency, high energy. Low frequency, low energy. That's for the entire spectrum. But really, all we're concerned with right now is the rainbow. That's what we're really concerned with. Now, what part of this is the rainbow? Roy G. Biv, Vib G. Yor? Okay. So if it's true that over here our radio waves have long wavelengths and low energy, and our gamma rays, and I'm opposite of you all, our gamma rays have high energy, short wavelength, then is it also true that violet has shorter waves and higher energy compared to red? You follow what I'm doing? Okay. So who is the highest energy color? Violet. All right. And the lowest energy color is? Who's the longest wavelength? Red is the longest wavelength, and violet is the shortest wavelength. How do you remember that? One of the easiest ways to remember that is if it doesn't hurt you, it's low energy. If it hurts you, it's high energy. Well, you're saying, well, colors don't hurt me at all. True, but let's go back to the whole spectrum. Do radio waves hurt you? No. If they did, we'd all be hurt. Radio waves don't hurt us. Microwaves don't hurt you. Now, yes, if you crawled in the microwave and somebody turned it on, you're going to boil your water. And you're a lot of water, so you're going to get hot. But it doesn't hurt you just being around a microwave. That's not going to hurt you. Infrared does not hurt you. So red is near infrared. That means it's low energy. Violet is near ultraviolet. Now, I like a tan, but I know it's damaging my skin. So does ultraviolet hurt us? Yes. So if it hurts us, it's high energy. So violet is near ultraviolet. And then, of course, we know X-rays. You can have too many X-rays, and gamma rays are definitely high energy and going to hurt you. So if it hurts you, it's high energy. That's how you're going to remember this. But still, you're thinking, what does this have to do with electrons? Well, I'm hoping you read the article that I told you to read. I told you to read the 3rd page of the fireworks article. So get out the page if you have it. If you don't, that's okay. I'm going to talk about it. Now, some of you may have felt like, man, I just wasted my printing or my ink or paper, whatever, printing this out. I don't care about fireworks, and I understand that. I only ask you to read the 3rd page. I hope you read the whole article, and I want to tell you why I include this in your notes. So much of the time, students in chemistry, whether it's this class, well, let me rephrase that. Students in non-chemistry majors in chemistry classes. Let me say it that way. Many times non-chemistry majors in chemistry classes feel like I might like chemistry, but what am I going to do with it? Teach? Well, heaven forbid, you might do that. But, you know, teaching is an option, I agree. But what can a chemist do? What can a chemist really do? That's probably what some of you think. I don't want to do research. Chemist is just boring. I wouldn't want to do that. I wouldn't want to do that every day. Well, one of the things that I think this article does a good job of is giving you a little bit of an insight into a really cool chemistry area, fireworks. Do you realize that behind fireworks there's a chemist? There has to be a chemist behind fireworks. Then you take that a step further and you say, wait a minute, if there's a chemist behind fireworks, then does that mean that explosions in general require some chemistry? Yeah. Well, then let's take that a step further. What about all like Hollywood movies? I mean, there's a lot of special effects that are dealing with fire that totally are explosions, but nobody gets blown up, really. Does that have something to do with chemistry? You mean there's chemistry in the movies? What about Epcot? What about Universal Studios? What about Disney World? Do you think there's some chemistry involved in all that? Yeah. Now, did you realize that before? Maybe not. And that's what I hope that something like this does. While I'm on that, just for a side, I want to mention something that if you ever have thought, you know, I kind of like chemistry. No, nursing's a great career. Don't get me wrong. Exercise physiology, exercise science, all those are great careers. But if you ever have thought, you know, I kind of like chemistry, maybe I would like to do something. Here's a field of chemistry that is so amazing, it's so large, and you probably didn't even think about it being chemistry, but now that I tell you this, you'll realize it. Cosmetic chemistry. Do you realize that is all chemistry? And you think, well, yeah, but what about it? There's all, you know, makeup, okay, big deal. Guys, it's not just makeup. Skincare products in general. And if you think I'm crazy, go to Walmart and look how many aisles are dedicated to cosmetics and skincare. It's huge. Cosmetic chemistry is huge. So if you ever are interested in chemistry, go to acs.org. That stands for American Chemical Society.org, and just do a search on careers, and you'll be amazed at the different things chemists can do. I think it's pretty cool. But that was an aside. Now, here's what I want to deal with right now. Why did I have you read this? Why did I have you read this? Well, it says beyond the basics. Well, what were the basics? If you had read the whole article, the basics were the booms and the bangs and the explosion. That was the basics. Now it says, so much for the basics. Now, what about color? There are other chemicals used to produce colors, but they only do their dazzling thanks to the first law of thermodynamics, which we have said is the law of conservation of energy, which says what? Is energy created? What is it? It changes from one form to another. Okay, so energy from the fire in the basic fuel is transferred to the atoms of the colorant chemicals. That excites the electrons. Now let's go back to Monday. At Monday's lecture, we said, where are the electrons in the atom? In general, where did we say they are? In the electron cloud, and some of you know that they're actually in energy levels, which we're going to get to today. But they're outside the nucleus, right? And so the energy from the fire excites those electrons, and they literally go further from the nucleus. So they literally get out farther from the nucleus into higher energy states. Then, though, there's a saying, what goes up must come down. Then, as the atom cools down, what happens to these electrons? They fall back down to a lower energy state. But if it took more energy to be out here, then what have they got extra of when they fall back down? Energy. And so as they cool down, remember, energy is conserved. It's never lost. It's just transferred. So as the electrons calm down, they give up energy in the form of light. And the color that you see is the light that you see from that fall. Well, what about the color? Well, what did we say Roy G. Biv was all based upon? Wavelengths. So certain colors give off energy at this wavelength. Some of them have energy at this wavelength. So depending upon what the energy is that's being given off will make the wavelength what it is, which makes the color what it is. So let's get this back down into where we're going with this, okay? So what do we have here in the atom? If I'm the atom, what's here? The nucleus, right? Who's here? Protons, okay? And then we have what? We have these electrons. Now, today we're going to find out that the electrons are really in 7 energy levels. And the first energy level is closest to the nucleus. And then the 7th energy level is farthest from the nucleus. Now, let's figure out right now, I'm just going to go ahead and explain this part to you. You told me that the nucleus is here, and what charge does it have? This is the positive nucleus. What charge do electrons have? Electrons are negative. So if I'm here and I'm negative, and this is a positive nucleus, does it take much energy for me to be here? No. Why not? What do opposites do? Attract. You with me? You played with magnets, right? When you get the magnets that are oppositely charged, if you get them pretty close together, what do they do? Snap together, don't they? They hold together because of that opposite attraction. So we have these electrons in the first energy level, and they don't take much energy to be here. It doesn't take much energy to be here because they're so close to the nucleus. Then we go out to a second energy level, third, fourth, fifth, sixth, and seventh. Now tell me about the 7th energy level. Does it take more energy to be here? Yes. All right, so now let's talk about getting excited. We're an atom, and we get fired up, literally, with fire. We got burned. We're getting burned. Or electricity. Now, folks, tell me something, and I wish to goodness I had this. It would be hilarious. If I had a button back here that I could push, and all of a sudden your seat started getting hot. Some of you, if I had a button that I could push and you didn't know it, but all of your seats started getting really, really hot. Some of you would be like, man, you'd be like jumping up and out of there. There'd be others of you that would be sitting there and you'd be like, it's kind of getting warm. Maybe it's getting a little bit warm. Do you see my point? Some of you would be like that. Well, it's the same thing going on inside this atom. So here's the atom. It's just in its resting state, hanging out. Everybody's just hanging out in their slow resting state here. Electrons are just happy. Then all of a sudden they get fired up. What do? Some of them go boom out here to the 7th energy level. Some of them, though, go, it's a little warm. But none of them can stay there. So then what happens is, let's say that these electrons jump from the 2nd to the 3rd and then fall back down. Are they giving off a lot of energy when they fall back down, or a little bit? A little bit. What color might that be? Red. Low energy. Now this one that got super excited, say we had a couple down here that got super excited and they went boom out to the 7th and then fell back down back to the 1st. That's a lot of energy given off, right? So what color might that be? You follow? Now what's so cool about all this? I'm explaining it to you knowing that electrons are in energy levels. But guess what? Niels Bohr and some other chemists and physicists, they figured out that electrons were in energy levels because they saw the colors of the flames. In other words, I'm explaining it to you backwards. They figured it out by just observing the colors, observing that there are different colors for different elements, and then figuring out those electrons must be in energy levels. Now, how did they do that? I don't have a clue. I'm just glad we now know so I can explain it backwards, because I couldn't have explained it the way they did. Do you follow what's happening? So now, let's put some words down in your notes. I've said the words, but I haven't really given you some notes. So let's write the words down in the notes. And then we're going to talk a little bit more about this, and then we'll move on. So I mentioned the word ground state. So let's write, what is the ground state? The ground state is when the electrons are in the lowest possible energy levels. When the electrons are in the lowest possible energy levels. The ground state is very stable. The ground state is stable. We will draw the electron configuration notations for the ground state. It is also called the resting state. Now, I realize at this moment you don't necessarily know what I mean by electron configuration notation. You will. That's the process we're going to use to draw these out. But we are going to deal with the ground state mainly. Your ground state would be when you're asleep. Okay, that would be your ground state. That, in essence, would be your ground state. The excited state is when the electrons are in higher than ground state energy levels due to being excited with fire or electricity. When the electrons are in higher than ground state energy levels due to being excited with fire or electricity. It is unstable. The excited state is unstable. When the electrons fall from the excited state back to the ground state, that energy is released in the form of colored light. When the electrons fall from the excited state back to the ground state, that energy is released in the form of colored light. So, to confirm, when do we see the color? When they fall. When the electrons fall.
Okay, so you know how like white is all colors? What is it when it's white?
What do you mean? What, like what element?
Like white is the presence of all colors and black is the absence of color. You know what I'm talking about? And like how like in elementary school we had like the glasses and like we had like a white light.
Okay, what you are talking about is a prism or a diffraction grating. And that is exactly what Niels Bohr and his other people used to separate the colors to actually see the exact energy transitions that were occurring. So what you're talking about is a prism or a diffraction grating actually takes the light from a rainbow, which is white light, and separates it into the different colors, which is what this is. This is white light. Now, and unfortunately, you cannot see this very well. Let me see if I can, no, it's just not, There, you can see it a little bit there. It's an overhead, so it's a little harder to see. But what this is showing you a bright line spectrum, meaning this is hydrogen's light that has been looked at through a diffraction grating or a prism and separated into the exact energy shifts, the exact energy falls that have occurred. When hydrogen's been excited and it's cooling down, there is a line here, and there is a line here, and there's a line there. Now, what's really cool is the fact that how many electrons does hydrogen have? 1. Now, how can there be 3 lines when there's only 1 electron? That electron's busy. And the other thing that you have to understand is we're not talking about 1 atom, are we? When you heat up something, you're not heating up just 1 atom. Are we heating up a lot of atoms if it's any element? Yeah, we're heating up a lot of hydrogen. We're burning hydrogen and looking at it through a diffraction grating. Our eye, when hydrogen burns, our eye sees blue. But if we separate that to see what true colors are there, true wavelengths of energy transitions are there, that's what we see. And that's showing the different shifts that are occurring. Helium looks like this. And it's, again, I think there's 5 transitions. There's 3 on this end that you can barely see, and then there's these 2. Now, neon, man, neon is awesome. Neon is just bonkers. It's all over the place. And there's only 10 electrons doing all that. It's just amazing how it can do that much. Now, there's something else in your world that not only is it fire that can cause these transitions, but what else? I've said electricity. So something besides fireworks where you've seen the same thing happen. Where else have you seen colored light? Neon signs. Neon signs. Neon lights work exactly on the exact same principle. These light bulbs in this room are fluorescent bulbs. The fluorescent tubes, that's what neon lights basically are tubes of glass. Now they're plastic too, but they're tubes with an anode and a cathode on the ends. And electricity is passing through that tube. And inside the tube, the first neon lights had what in them? Neon. Come on, that's like common sense, okay? The first neon lights had neon in them. And neon actually glows, in your eye sees bright orange. That's what neon is. Bright orange. But if you break that down, is there a lot more going on than just orange? Yeah. And so think about those first neon lights. Up until that point, we had just basically white light. Can you imagine how just transformational that was for signs? To have all of a sudden this bright orange light? I mean, that was like, whoa, that you could see that then, and then it just has expanded since then. So what have they done to make all the different colors of neon lights? What do you think now that you know how they're made? Neon's bright orange. They put different elements in those. And then they went further and they mixed elements. And then they went even further and they colored the glass too. And that made it probably cheaper. Does that make sense though? All of this. Now, go even today. You could go to Lowe's. You could go to Home Depot and you walk through that aisle of fluorescent lights. Go to an old building on campus and you can see the same thing. This room is pretty much the same. But if you go through a fluorescent lighting area and you look at them and you just kind of step back and look, that one's a little more purple and that one's a little more orange and that one's kind of yellow. Well, that one's just white. Do you know what I'm talking about? The different colors? Okay, now go to how they write the names on those bulbs. Warm light, daylight, cool light. You follow what I'm saying? So they've taken all this knowledge now And if it's a more red or orange, they call it warm. If it's more blue, they'll call it a cool light. And that's where all that comes from. But what makes them the different colors? The element that's in them. Does that make sense? So all of this has come from the basic principle of electrons getting excited. That's all of it, is from electrons getting excited, jumping to higher energy levels, and when they fall, they give off the color. All of this has come from that. Okay? Pretty cool. And like I said, we know this now, which is what's going to help us understand all of this about where the electrons are in the atom. So I have basically spent that time to get you to the point of now, okay, we know electrons are in energy levels. And so we're going to look at the entire electromagnetic, or I'm sorry, not electro, we've already looked at the electromagnetic spectrum. We're going to look at what's called the quantum theory. And the quantum theory is basically a theory that describes the location of the electrons, and it uses numbers and letters. And guys, I want to tell you right now, do not get caught up in the wording of this, because you could go crazy just because they call them quantum numbers, but they're really letters. Okay, so that's confusing. Don't get confused by it, okay? What these quantum numbers or letters do is they tell the location of the electron with respect to 4 different things. And these are the 4 things that they're telling us. The distance of the electron from the nucleus, the shape of the electron orbital, the position of the electron with respect to the 3 axes in space, and the direction of the electron spin. Now we're going to spend most of our time on these 2, but I actually want to talk about these 2 first because I want to get these out of the way, and then I'll just mention them in a minute and it will make sense. I want to deal with this one first. How many ways can things spin? 2. Now here's what's funny. When you think that, well gosh, they could spin all kinds of ways. But then when you start to think about it, no, they can't. I mean, I can do this, and you say, okay, well, go the other way. Well, I am. I mean, but am I still spinning the same way? Yeah. So there's just 2 ways, this way and that way, right? That's it. That's the only 2 ways things can spin. So there are only 2 directions things can spin, and that's called clockwise and counterclockwise. Now, why do I mention that? Because electrons exist in pairs, but electrons are negative, correct? What do like charges typically do to each other? Repel. But I just said electrons exist in pairs. So how do they exist in pairs? They're spinning in opposite directions. If they're spinning in opposite directions, then can they exist in pairs? And then if they get near, what do? Boom. They're going to repel, but they're going to spin in opposite directions still. That's how you have a pair of electrons. And a lot of what we're going to do will be dealing with pairs of electrons. And so the fact that you can have a pair, it's due to the fact they're spinning in opposite directions. That's how. Then you've got that scenario of the position of the electron with respect to the 3 axes in space. All right, let's deal first. What are the 3 axes in space? Come on. Thank you, Travis. X, Y, and Z. Thank you. X, Y, and Z are the 3 axes in space. You with me? Have you graphed lately? Okay, X, Y, and Z are the 3 axes in space. So you've got X, Y, Z. You with me? You got to know that. Okay. So we'll deal with that in a minute on that position, but just remember there are 3 axes, X, Y, and Z. So now let's go to number 1. That's where we're going to focus. We're going to focus on the principal quantum number and the orbital quantum number. That's our main focus. So let's talk first about the principal quantum number. And the great thing is I've already talked about it today. The principal quantum number is basically the energy level. If I had one word I would say remember here, or one phrase, it's called energy level. The principal quantum number is the energy level. And there are 7 energy levels. Now look at your periodic table from last day and tell me where you see 7. The rows? Do you see 7 rows? Did you number 1 through 7 for your periods on the periodic table? All right, guess what? Those periods are energy levels. Those are the energy levels. And if you have electrons in the first energy level, I've already done this today, right? If you have electrons in the first energy level, tell me about them. Close to the nucleus, farther away from the nucleus? Close to the nucleus. Take a little energy, a lot of energy to be here. A little energy. 4, 5, 6, 7. Now, this is, I don't have this. I wish I did because I think it would be so helpful. Imagine if I had a thing that went over me that was a series of hula hoops. Can you visualize that? That's what I'm visualizing when I'm doing this. Okay? So first energy level, second energy level, third, fourth, fifth, sixth, and seventh. So the 7th energy level is way away, right? It's far away from the nucleus. Does it take a lot of energy to be out here? Yes, because there's not much attraction between those electrons and the nucleus. You with me? Okay. How will you know what energy level your element has electrons in? You know it by what period it is in. So if you look up at your periodic table, you've got your periodic table there. Look at your periodic table, and the highest number of energy levels that your element has electrons in is what period you are in. So let's just take sodium first. That means sodium has electrons in how many different energy levels? 3. Yes? Tell me about selenium, Se. Selenium has electrons in how many different energy levels? 4. Everybody with me? What about tin, Sn? Tin has electrons in how many different energy levels? So everybody's following. Okay. So you'll know how many energy levels your atom has electrons in by just simply the period that it's in. So we've got a little bit of knowledge now on where these electrons are, but we have to find out what are they doing. So they're this far from the nucleus, but how many are there and what are they doing? That's the question now. And that is answered with the orbital quantum number. The orbital quantum number indicates the shape that the electron is traveling in, basically. It's the path that the electron is traveling in. I will call it mostly subshell. If you hear me say subshell, that's probably what I will call it most often. Sometimes I will say shape, but usually I will say the subshell. The subshell can be one of 4 things: S, P, D, or F. Now what I'm saying is, let's take, and I did this on purpose, let's pretend that right here is the nucleus, okay? This is the nucleus of the atom. Now, right now, I'm traveling around the first energy level. You with me? And what I'm doing is the sphere, meaning I'm going in a spherical shape. Now, I know I'm going in circles, but pretend with me here, okay? So I'm going in the sphere. The sphere is the S quantum number, or S subshell. And it doesn't take much energy to do the sphere, does it? Then the question is, how many electrons can do the sphere? What's it say? 2. Now let's think about that for a minute. So within this space, in the first energy level, we've got the sphere, we've got the ball. Why can 2 electrons do that? Because they're spinning in opposite directions. Because if you think about this, this is all three-dimensional, and that's why my little explanation this way is not the best. Imagine X, Y, and Z. Now, I can't do this perfectly. Am I somewhat right? The pencil is one of my, there, is that, I'm still not right. That's hard to do, just so you know, okay? Am I somewhat right? Is that kind of like X, Y, and Z? Okay. Imagine a ball in the center of that. In other words, now let me take this. Here's my ball. I stick it in this way. I stick it in that way. I stick it in that way. There's only one way that ball can go on X, Y, and Z, right? You follow? So there's only one position that S can have, and how many electrons fit in it? 2. Why? Because they're going in opposite directions. P is the second type of shape. But in the first energy level, you can only have S. The second energy level has S and P. And 6 electrons can fit in P. Now the question is, okay, why can 6 electrons fit in P? P is a figure 8. You follow what a figure 8 is? Just draw an 8. That's a figure 8, and P is a figure 8, and it can hold 6 electrons. So let me explain to you why it will hold 6 electrons. This is the x-axis, yes? This is an electron along the x-axis. You with me? Now watch. I'm talented, aren't I? What am I doing? Why am I doing this? What am I trying to show you? 2 electrons on the x-axis in P going in opposite directions. You with me? Now, I can't do it this way. I've tried and I can't get it. Okay? But you with me? So how many would be there? 2 more, and then same thing here, right? 2 more. So total how many? 6. Do you see why it's 6 now? And then you can keep going. D says that it has 10 electrons in D. Guess how many positions there are? 5. Why? Because 2 in each position. F says it has 14 electrons. How many positions are there? 7. You follow? Because 2 electrons in every position. And I'm not going to even expect you to know how many positions there are. But it makes sense when you understand it to help you remember why there are 6, especially for the X. That one makes sense because you can see it. How do you know how many subshells will be in the energy level? This sentence tells you right here. The number of possible subshells in an energy level is equal to the value of the highest energy level. The number of possible subshells in an energy level is equal to the value of the highest energy level. That means in energy level 1, you can have how many subshells? 1. Who is it? S. How many electrons fit there? That's the 2 part. In energy level 2, how many subshells are there? 2. Who are they? S and P. In energy level 3, how many electrons are there? Or how many subshells are there, rather? Who are they? S, P, and D. Energy level 4 can have S, P, D, and F. And then you're saying, but wait a minute, there's energy level 5, there's energy level 6, there's energy level 7, and you just said S, P, and D, and F are it. It will work. I'll show you it'll work. But guess what? The beauty of all this is you don't have to memorize all this. That's the glory of it, because your whole periodic table is laid out perfectly without you having to memorize anything. So pull out the clean periodic table, and I want you to look at the periodic table, and I want you to tell me, just by looking at the periodic table, I want you to tell me where are some logical breaks in the periodic table. So if I said to you, okay, I want to know some logical breaks, I'm just going to throw some things out here. Is this a logical break in the periodic table? No. All right, what about right here? Is that a logical break in the periodic table? All right. Tell me where a logical break is in the periodic table. Give me the elements between blank and blank. Barium? Right here? And? Just give me the symbol. Lu? Is that a logical break? In other words, right there, is that a logical break? Yes? Where's another logical break? Right here, is this a logical break? Now, count how many columns you put in this break. Come on, that's not hard. How many columns are here? 2. How many columns are over here? 6. Count how many columns you just put right here. 10. How many columns then are down here? 14. Where have we seen 2, 6, 10, and 14 before tonight? Wow, isn't that just handy? 1, 2, 3, 4. So guys, guess what? Your whole periodic table is laid out. These 2 columns represent the S subshell. These 6 columns represent the P subshell. These 10 represent the D, and these 14 represent the F. So as long as you can count to 14, you can do this. And I'll let you take one shoe off, as long as you've washed your feet and your shoes lately, if you need your fingers and toes to count. Okay? So 14 is the maximum you have to count to get this. Couple things I want you to do, though. I want you to pull helium over here. Because really, helium only has 2 electrons. And since it has 2 electrons, it's going to put them in the first energy level S subshell. It's not actually going to put them in P. Wake up back in the back. Your friend's about to fall off the chair. Wake up. You're in your resting state. Let's get you excited a little bit, okay? All right, so we've got the S subshell here. P is here, D is here, and F is at the bottom. Now then, on the left side, what did I tell you to label these for? So go ahead. What do we put? And if it helps, I would probably go ahead and number this side as well, just so that you have a visual on both sides. Couple more things I want you to label, and I'm going to preface these labels with this comment. I promise you, I will tell you why I'm doing something. But for the beginning, I don't do this, but one time a semester, I normally am really good about telling you why, but this one time, to start with, I want you just to do it. Don't ask me why for starters. Just do it. I'll explain the why, but starting out, just do it. Here's what I want you to do. I want you to put 3D here. You thought it was going to be 4D because this being 4. But I'm telling you this is 3D over to zinc. Below this, put 4D. Then 5D. And then 6D. I also want you to make a note, 56 is barium. When you get to barium, instead of going on across, look at your numbers. Barium is 56, then this is what? This is where you have to come down. So 56 is going to come down to 57, and even though it pulled out of the 6th period, this is where you will fill in for F. Again, I'll explain why later. Just do it now. Over here, you do 70 and then make a note to yourself. Go to 71, which is 5D. '88 comes down to 89, and that is 5F. And then when we get to the end, 102, go to 103, which is 6D. What this is telling us is where the electrons are in the atom. And not only where they are, but what they are doing. Okay? So there's how far from the nucleus and what are they doing in that distance from the nucleus. That's what this is telling us. How do we write this? Well, let me tell you what you would say if you were to write this sentence. Hydrogen has 1 electron. Do you agree with that statement? Hydrogen's 1 electron is in the first energy level, S subshell. Everybody agree with that statement? So if I said to you, I want to know about lithium's electrons, then you could say to me, lithium has 3 electrons. There are 2 electrons in the first energy level, S subshell, and there is 1 electron in the second energy level, S subshell. Does that make sense, what I'm saying? All right. Would you want to write those words out every time for something that, say, that had 51 electrons? No way. That would be like a whole page of writing just to tell me about where those electrons are. So instead, we have what is called electron configuration notation. And electron configuration notation is a method of indicating the location of the electrons with respect to energy level and subshell. So all we're talking about is energy level and subshell and the number of electrons that are there. So the complete electron configuration notation for hydrogen, we say this 1s1. That is the complete electron configuration notation for hydrogen, 1s1. Now what does that mean? The big 1 is the energy level. The S is the subshell. And the superscript 1 is the number of electrons in that subshell. So I'm going to write over here, I'm just going to repeat 1s1 for hydrogen. That is hydrogen's electron configuration notation, 1s1. Now when you're writing these, make sure that your big number is a big number. Make sure that your letter is lowercase and small, and that your superscript is a superscript on the S. Don't make them all one size. It's really hard to read, so make them in this kind of dimensions. Helium, I told you, should be shoved over next to hydrogen. Why? Because how many electrons does helium have? 2 electrons. Helium has 2 electrons. Now, how many electrons can the first energy level hold? 2. Why? Because it only has S, and S holds 2. So to write helium's electron configuration notation, we write 1s2. 1s2. That is helium's electron configuration notation. 1s2. Now if you remember, helium is over there on the noble gas column. Why is helium a noble gas? It's stable. How many can fit in the first energy level? 2. Does helium have a full first energy level? Yes. It doesn't need any more electrons. It's happy. It has its 2. It can't hold any more because it can only hold 2. That's why helium is over there, and that's why it's a noble gas. Why is hydrogen over here with the metals even though it's a nonmetal? Because how many electrons does it have? 1. And it only has 1 energy level, and it only has 1 electron in that energy level. That's why it's over there, which tells us what the next one will be in the end that we write. Lithium has a total of how many electrons total? 3. In order to get to this second energy level, where do you have to pass through? The first energy level. And most of the time, you'll fill up that energy level before you get to an outer energy level. So we have to put 2 of lithium's electrons in the first energy level, S subshell, and there's 2 of them there. But then where is the last electron? Second energy level, but look where it is. What subshell? It's still an S because, guys, is this the same S? It's a different S. Why is it a different S? Because it's in a different energy level. Now that throws some of you off, so let's talk about that for a minute. Let's talk about what's going on. First energy level. The only path you can travel in the first energy level is what? The sphere. Okay? That's what I'm trying to do. I'm doing circles, okay? So that's the only path you can travel in this space from the nucleus. You can only do the sphere. But I'm farther away from the nucleus. Again, picture that bullseye. Picture the space between the 2 hula hoops. You with me? The second energy level. Picture that with me. Within that space from the nucleus, within that distance from the nucleus, 2 of the electrons will be doing the sphere, and 6 will be doing the figure 8. Yes? Then as we go out to the third energy level, within that space, again, 2 will be doing circles or spheres, 6 will be doing figure 8s, and then 10 will be doing the clover leaf. Yes? So that's why every energy level has an S. The second and beyond all have S and P. Third and beyond all have SPD. Yes? You with what's going on? Okay. Now let's look at this again. We say 1s2, 2s1. Are lithium and hydrogen one on top of each other on the periodic table? Yes, they are, aren't they? Think that in your head, in the back of your mind for just a minute. Let's keep going. Write down the first 10 elements. So there's sodium. I'm sorry, no, that's not sodium. Beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. What will beryllium be? What will we write for beryllium? 1s2, 2s2. Why? How many electrons does beryllium have total? 4. Where are the first two? First energy level, S subshell. Where are the next two? Second energy level, S subshell. Go to the next one, boron. How many total electrons does boron have? 5. Where are the first two? First energy level, S subshell. So we put 1s2. Now somebody wants to say this, so I'll say it for you. Does that mean everybody past helium has 1s2? Yes. Do you see that? Everybody past helium starts with 1s2. Everybody past helium starts with 1s2. So 1s2, then what do we write? 2s2. Are we still in the second energy level? Yes, we are. Look where you are on the periodic table. Are you still in the second energy level? So still 2, but now we flipped over to which subshell? P, and how many electrons are there? 1. Let me show you on the periodic table what we just did. This is boron right here, okay? So we did 1s2, 2s2, 2p1. Yes or no? Okay. Now you write carbon. What will carbon be? 1s2, 2s2, 2p2. What will nitrogen be? 1s2, 2s2, 2p3. Now, somebody wants to say, well, why don't you say 2p1, 2p2, 2p3? Think about it this way. If I said to you, I had 3 cookies before class, would I say to you, I had 1 cookie? I had 2 cookies? I had 3 cookies. No. I would say I had 3 cookies. Do you see my point? You don't say every cookie you had. You say I had 3 cookies. That's the same thing here. You would say 2p3 because there are 3 in P. Oxygen, what's oxygen going to be? 1s2, 2s2, 2p4. Is it making sense? You do fluorine and neon. Do the whole thing for fluorine and neon. All right, what is fluorine? And neon? What is neon? What type of element is neon? A noble gas. Why is it a noble gas? It's stable. Guys, what is the maximum number of electrons that can fit in the second energy level? 8. Because the second energy level has an S and it has a P. So how many electrons total fit in the second energy level? 8. Does neon have 8? Yes. So is it stable? Does it need anybody else? No. That is why it's a noble gas. All right, before I have you do any more, which we're going to do plenty, I want to show you, I want to say to you and show you at the same time the entire periodic table. I'm going to say the electron configuration notation for all the elements through UNE 109. Okay? I want you to follow along with your eyes and even say it if you choose to. That helps. That's how you'll learn best. With me as I do this so that you start to see what's happening. Now remember, I've already told you when you get here it's 3D, not 4D. I will explain why later, but right now you just do it, okay? So I'm going all the way down to 109. 1s2. Before I keep going, though, I need to say this. I haven't said it, I don't think, but I need to say this because it's an obvious to me, but it may not be to you. The way you read the periodic table is like you read a paper. How do you read a paper? Left to right, down. Left, right, down. You with me? That's exactly the same way you read this. Notice the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Do you see what's happening? 18, 19. Do you see what's happening? And then down here, I tell you where to find the next number. So you read the periodic table just like you read a book. So now then, let me start again. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, put your phone up, all the way, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 5f14, 6d7. Do you follow? Is that making sense? Now we're going to do several. Before we start, I want to ask you something. Some of you have done this in high school, and that's great. If you did this in high school and your teacher gave you or had you write down on a sheet of paper 1s, 2s, 2p, 3s, 3p, 3d, 4s, if your teacher did that, does anybody know what I'm talking about? Do not use that. That is a silly, crazy thing to do. It's just something else for you to learn that you don't need. Don't do it that way. If you try to use that, you're not really getting it. You're just following what they told you to do. Learn how to do this with only the periodic table. If you learn it this way, then if I say to you, I want to know who has electrons in their last configuration that you write, who has the last configuration notation 3d5. Give me the symbol of who is 3d5. Mn. Do you see that? Who is 6p2? Lead. Do you see that? Who is 5s2? Strontium. Okay? Any of these you should be able to just immediately pull out if you know how to do it with the periodic table. So now let's do some more. This is my favorite lecture of the semester because you're going to sing to me. Okay? And if you don't sing well enough, we will keep doing this as long as we need to. So you have to sing well, and you're on film tonight. So this will be an awesome lecture for my grandkids will get to hear you sing, okay? How special that is for you all. So, if I ever have grandkids. Okay, so let's look at some. Let's start off easy. I want you to write the configuration for magnesium, Mg. Start off 1s2, 2, and now just write it, and then you'll sing to me in a minute. Just write it. Don't try to do it from memory. Have your periodic table sitting there next to you. Follow it, left, right, down. Exactly, and then what's next? 2. All right, so what did you get? 1s2. Yes or no? Wimpy singing, but it's right. You'll get better. The longer they get, the better you get. Yes or no, though? All right, let's up it. Let's do, let's just go for it. Titanium. Do titanium. Now, I want to tell you right now, don't use this periodic table. Always use the one you have in front of you. Because when we get down to the bottom, it's going to be wrong up there. So always use the one I give you. Use it now. Just get in the habit of using the one that I give you. Are we ready? Okay, so titanium. 1s2.
2s2, 2p6, 3s2, 3p6, 4s2,
3d2. Yes or no? Somebody said no. Let's look at our periodic table. Here is titanium right here, Ti. Okay? So when I'm doing this, I would put my finger here, then I'd go back to the beginning. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Yes or no? Now, I want to go back to one that you just did. Before titanium, you did magnesium. What's the last thing you wrote for magnesium? What's the last thing you wrote for beryllium? What's the last thing you wrote for helium? What's the last thing you're going to write for strontium? What are you finding out? Are they all in the second column? Which means what? They're all going to be what? S2. Yes? All of this column is going to be S1. Yes? This column's all going to be what? Yes? And what did we say about families? They all have similar characteristics? That's one of them. The whole periodic table is laid out beautifully. And it was done this way on purpose. The designers of the periodic table actually laid out the periodic table because these elements had similar characteristics. And then later they found, they didn't even know some of the characteristics. Then they found out what the characteristics were after they laid it out this way. And this is one of them. Okay? You also know this entire family has a charge when it becomes an ion of what? +1. This entire column has a charge of? Okay. Over here, what is this column? -1. -2, -3. That'll come into play in just a minute. Let's do some more. Let's do antimony, SB. Do antimony, SB. Are we ready? We got SB? Now, I was looking at my paper. This morning, I did SB, then there were two others that I did, and they were singing well enough. Now, I'm not feeling that you're going to be there yet, but so show me, okay? Show me. And we're actually going to do this. We're actually going to split you up. This half of the room is going to do SB. Okay? You all don't say anything. Don't help them out. Okay? So it's this half of the room. Now, lots of times I will do guys and girls. That's not quite fair, but I love to hear the men sing. So I might do that tonight, okay? So we're going to do SB, this side of the room only. Are we ready? Got it? Okay. Huh? No. Okay, you ready to do it? All right, 1S2.
2S2, 2P6, 3S2, 3P6, 4S2, 3D10, 4P6, 5S2, 4D10, 5E3.
Yes or no? What was the last thing you wrote for nitrogen? Does that make sense that it should have been 2p3 and this should be 5p3? Does that make sense? Okay. All right. Here's one of my corny bad jokes. If you have a lisp and you want to tell someone to get out of your business, what do you say? Get out of my bismuth. So do bismuth. Bi. It's bad. Do bi, bismuth. Bi. I only have like 3 of those, so you don't have to deal with that much, okay? So bi, bismuth. And I apologize if you have a lisp. That was not intended to be bad for you. Can somebody tell me where the sign-in sheet is? Has everybody seen the, just send it down. Has everybody seen the sign-in sheet? Has anybody not seen the sign-in sheet? Thank you. Just a reminder about the attendance policy. Obviously, if you're here, and that's wonderful. But we do have an attendance policy. Your grade will be lowered no matter what the excuse, if it meets past the number that you can miss. So make sure you read the syllabus again. All right, bismuth, are we ready? Nope? Yes, no? No? All right, finish it up. Okay, let's go. This side of the room. Only this side of the room. Don't help them out. And I am going to make you guys do one in a minute. I have to hear it this year. I'm sorry. I only had like 2 in my class this morning, so I couldn't do it to them. All right, you on the left, all of you on the left, give me bismuth. 1s2.
3S2, 3P6, 4S2, 3D10,
You had to go down and come back up. Why did you have to do that? Because, look, you had to follow 56 down to 57, all the way down, and then come back up. Okay, did you get that? All right. What do you do with a calf at a rodeo? What do you do with a calf at a rodeo? You rope him. EU. EU. All of you do EU, but guys, you get to be Europeum that calf. All right? EU. EU. All of you do it, and then the guys are going to sing to me. Dakota, you need to help them. And if the guys do a good job, we'll stop. Not stop, but stop this. So we're counting on you, man. EU. Travis, you help him too. Did you get it? Are you getting it? All right, gets pretty long, doesn't it? Have we got it? The whole thing? Men, are you ready? There's 10 of you. No pressure. Do you have questions before you sing, men? No, let me ask you this. Did you go down? Okay. So you went down, but you don't come back up. Right? Okay. Did you go down, but you didn't come back up? Back in the back row? So we ready? I want to hear my bass singers now. Okay? They're going to sing like this. All right, are you ready, man? 1S2.
2S2, 2P6, 3S2, 3P6, 4S2, 3D10, 4P6, 5S2, 4D10, 5P6, 6S2, 4S7.
Good job. Somebody had a good bass in there. That was nice. Thank you. That just makes my year. I live for that. It wasn't as good as I wanted, but it's okay. You were good. It wasn't as loud, but it was good. So are you getting it? Isn't that cool? Every one of you got it. Okay? Everybody can usually get it. That's good. Now, here's the question. Do we have to write that whole thing on the test? That's what you're thinking. I think my teacher taught me a shortcut. Well, there is, and I'm going to teach it to you right now. Why didn't I teach you that first? Because if I taught you that first, you wouldn't have had a clue what you were really doing. So what is the shortcut? The shortcut is this. Complete electron configuration notation is what all this is, okay? So compare that to noble gas or abbreviated configuration notation. What is that? Well, use the symbol of the previous noble gas in brackets and then proceed. Now, you really don't even have to write that statement down because you're going to do it and it makes sense. But what is it? That's what it is. You use the symbol of the previous noble gas, put it in brackets, and then proceed. So let's do one of the favorite scientists of all times. Who is that? Einstein. ES, number 99. So find Einstein down here, number 99, and find the previous noble gas for Einstein. Einsteinium, actually. Who is the previous noble gas? Radon, Rn. So you put Rn in brackets. And then go. So who comes after radon? 7s2, and then what? 5f, 11. And that's all you have to write. And you're like, gosh, that's a lot easier. Well, why does that work? Because, did you realize going through here we were just repeating ourselves? And so once you get to the noble gas, what you're saying is everything up to this noble gas is full. You can't put anything, it's all full. That's why you start at the previous noble gas and then you proceed on, because that's what changes. It's past the noble gas that changes. So let's do another one. Let's do germanium, Ge. Who is the previous noble gas for germanium? Ge. Argon. So you put argon in brackets. And then what? 4s2, 3d10, 4p2. Do you see that? Let's do one more. Let's do gold. Do gold. Au. Who is the previous noble gas for Au? Xenon, Xe. So now proceed from there. Now be careful on this one. Follow your numbers. So after xenon, what do you put? Very good. Yes or no? Does that make sense? Okay, now there's two more things. We're not done. There's two more things. This is like the climax of the day, okay? There's two things. The first is not, and then the last thing will be. The first thing I want to explain to you is I told you just do this going back to the 3D instead of being 4D. Just do it. That's why I told you earlier. Now I'm going to tell you why it does that. There are two factors going on with energy, and electrons fill up with lower energy positions first. But there's two things that are affecting energy. One is the distance from the nucleus, right? Closer to the nucleus is lower energy, farther from the nucleus is higher energy, yes? Okay. The second thing, though, is what are you doing? You with me? So there's two things, there's two factors that affect the amount of energy it takes. It actually takes less energy to go into the fourth energy level and do the S shape than it does to stay in the third energy level and do the D. That is why you go 3s2, 3p6, then 4s2, then back to 3d. So if I were showing this like so, here's what would happen. You fill up 2 electrons in one first energy level and what they're doing the S, yes? Then you go out here to the second energy level and you do the S, and then you fill up 6 with P. Then you go out to the third energy level and you do the S, you do the P, then you go to the fourth energy level and put 2 electrons in S. Then you come back down to the third energy level and do that 4-leaf clover, D. Then you go back out to 5P and do P. Then you go all the way to 6S. Then you fall way back to 4F because it's easier to do 6S than it is to do 4F. You see what's happening? And it's all because of energy. If that doesn't make sense, let me explain it in this manner. There are 2 jobs on our farm that have to be done every day. One of them is to go to the barn and feed the dog. The other one is to go out to the chicken house, and I want you to go get the eggs, make sure they have water, clean up the poop off the floor, and then come back to the house. Now here's the kicker. The chicken house is closer to the house. The barn is a lot farther away. It's like 3 times as far to the barn as it is to the chicken house. Which job do you want? I can't believe you want the chickens. Most people say they want to go do the dog. Most people say it would take less energy to do what? Go farther away to do the easier job. You follow? That's exactly what we're talking about here. Yeah. Isn't that cool? Chickens and dogs and chemistry. I mean, it's cool, isn't it? So, all right. Does that make sense now? If it doesn't make sense, then just do it. Okay? Just 4s2, 3d10, and then keep going. Just do it. All right? Now, why did I spend almost 2 hours teaching you this? Here's the ultimate end of why I did that. Valence electrons. And then we're going to say ions. Valence electrons, and then we're going to talk about ions. Valence electrons are outer energy level electrons. Valence electrons are outer energy level electrons. They play the role in forming compounds. Valence electrons play the role in forming compounds. Monday, I'm going to tie up loose ends from the videos that you are going to watch before Monday about nomenclature. And nomenclature is putting electrons together to make compounds, in essence. That's what it's doing. Because it's really putting atoms together, but who plays the role in forming those atoms to make compounds? The electrons. And electrons are either lost or they're gained or they're shared. Now today I'm going to focus on that losing or gaining of electrons. I'll deal with sharing next week, probably Wednesday, but right now I want to deal with losing or gaining electrons. Valence electrons are outer energy level electrons. So I want you to go back to these electron configuration notations that you wrote, and I want you to tell me, I want to do the 2 obvious ones first, then I'll keep going. Hydrogen has one valence electron because it only has one electron, right? And where is it? In the first energy level. Helium has two valence electrons. It has only two electrons. Now lithium, how many outer energy level electrons does lithium have? One. How many outer energy electrons does beryllium have? Two. How many outer energy level electrons, now be careful here, how many outer energy level electrons does boron have? Energy level. 3. Why does it have 3? Because it has 2 in the S and 1 in the P. How many outer energy level electrons does carbon have? 4. How many does nitrogen have? 5. Oxygen, 6, 7, and 8. Now, I'm going to skip, and remember earlier we talked about nitrogen and antimony being in the same column? Now, tell me what is, now answer my question, what is the outer energy level of antimony? Energy level. 5. Everybody with me? 5 is the outer energy level. How many electrons are in the outer energy level for antimony? 5. Because look, there are 2 in S and there are 3 in P. Well, now, didn't you tell me that nitrogen also had 5? So wait a minute. Are you telling me that everybody here has 5 valence electrons? Yes. Tell me about this column. Everybody has 1 valence electrons. Don't put your stuff up yet. Please wait for me. Everybody here has 1 valence electron. Tell me about this column. 2 valence electrons. What about this?
3, 4, 5, 6, 7, 8.
And then helium only has how many? 2. But it's here because it's got a full outer energy level. Now then, the whole purpose of tonight's lecture, of going through all this, is to get you to this point where now a light bulb hopefully will come on, because you just told me that this entire column has 1 valence electron. And I told you earlier, either Monday or Wednesday, I can't remember, that this entire column, when it becomes an ion, has a charge of +1. How did it get a charge of +1? It lost an electron. Now, here is the whole point. Why did it lose an electron? Why did lithium lose an electron? Because it was on the outer energy level, and by losing the 1 electron, who does it now look like? Helium. Are noble gases stable? Yes. Now let's go down farther. Potassium also can become an ion with a +1 charge. When it loses its 1 electron, who does it look like? Argon. Is it stable? Yes. Now go to the +2 column. What do they do to become more stable? Lose 2 electrons, so they look like the previous noble gas, yes? Because who's stable? The noble gases are stable. Now let's flip to the other side. Fluorine. It gains 1. Who does it gain 1 to look like? Why? Because it's more stable. So is the goal of forming compounds to become more stable? Yes. Guys, do you all have a clue how much chemistry in real life goes together? Do you realize, and I've never said this before, but it just hit me tonight, I sometimes have these moments. You all are a generation, many of you will live together before you get married, and maybe never get married. Compounds are marriages. Compounds are more stable because there's a commitment. Now then, some of you didn't grow up with compounds that were stable, though, and that makes a problem. But let's go back to the chemistry for a minute. And this also goes with, this is something I have said before. Go back to my picture of the hula hoops. Rubidium down here has how many valence electrons? 1 valence electrons. What charge would rubidium have? When it becomes an ion, it would be what? +1. Where is the electron lost from? The outer energy level. Where is it easier to lose an electron from? The outer energy level. Now, why is that? What charge is this? What charge are these? Okay, if I'm holding on to something and I want to really hang on to it, do I hold it onto it like this? Yes. Your mama used to hold you like this. She didn't want to lose you. And then you grew up and you came to college. You're no longer close to the nucleus. Some of you have done some stupid things already, and some of you will do some stupid things. Because guess what? You're not close to the nucleus, and the nucleus isn't holding on to you as tightly. Some of you are going to find spouses while you're at college, and that's okay. That's a good thing. Why is that? Because if I want to get rid of something, where do I put it? Outside the nucleus. Does that make sense? So right here, rubidium has how many valence electrons? 1 valence electron. Is it close to the nucleus? No. In fact, here's the scenario. Let's just take potassium. Let's take potassium, number 4, or 19 rather. Potassium. Potassium has 1 electron in its valence shell. Potassium, now this is it, guys. This is the ultimate right here, if you get this. Potassium, walking down the street one day, and it has 1 electron out here in its 4th energy level, just by itself. Well, iodine was walking down in the other direction. And iodine had 7 electrons in its outer energy level. What happened? Potassium said, man, I'd really like for you to have this electron. And iodine said, man, baby, I would love to have your electron. And guess what they made? Potassium iodide. How sweet is that? All of that is to get you to the point of understanding how many potassiums did it take? 1. How many iodides did it take, or iodines? 1. Why? Because potassium had 1 electron to give and iodine needed 1. Now, it's not always going to be a 1-to-1 like that. Sometimes it's going to take, for instance, in potassium, and I won't get kinky on this one, on potassium, it only has 1 electron, right, that it needs to lose. But look at sulfur. Sulfur would really like to gain how many? 2. So guess what? It's 2 potassiums that go with 1 sulfur. And that's why the formula is K2S. Now, when you're watching those nomenclature videos, if you haven't, and I haven't expected you necessarily to have watched them by now, hopefully when you're watching that, that's going to make sense. And that was why all of this was for tonight, was to get you to that point.
What is the charge of all the elements that are like in a specific...
They don't have a fixed charge. If I haven't told you the column, it doesn't have a fixed charge. Okay? All right, guys, watch those videos, and I'll see you Monday.